Welcome back, this is Andrew Homer, London Brookes College. I want to revise the shapes of covalent molecules. Covalently bonded materials are non-metal atoms joined together. Okay, a covalent bond is a shared pair of electrons. One atom contributes an electron, the other one contributes another one, and they share it. That's a single covalent bond. The point of this talk is not to talk about the detailed bonding, but the shapes involved. Most covalent molecules are simple materials, simple little molecules like carbon dioxide, CO2, water, H2O, methane, CH4. There are a small number of what we call giant lattices. There are very big covalently bonded materials. This one here has this beautiful regular arrangement. This is a diamond structure. It's tetrahedral, and if you have a diamond in a ring, that is literally one molecule that fills the whole stone. Okay? It's continuous bonding throughout. Very valuable, very expensive, and the hardest natural material on the planet. Much more common is the other type of carbon. This is graphite. The atoms are absolutely identical. It's just, I've just organized them into a different arrangement here. This is graphite with the well-known hexagonal holes, hexagonal plates, and between these layers we've got the weak van der Waals forces enabling the layers just to slip off. Imagine a pile of paper sliding off a desk. When you write in a book with a pencil, the layers slip off onto the paper. These are giant structures. They are not the typical arrangement for covalent bonding. It happens particularly with carbon. Something that's very exciting that was discovered in 1985, and what is amazing, this is actually when I started teaching, this hadn't been discovered. 1985, this was discovered. This is a C60 carbon molecule. If you look at that closely, you look at the arrangement there, and it should start to ring a bell. What does that remind you of? This is an authentic C60 molecule. It's known as Buckminster fullerene, or buckyballs for short. It's named after an architect, American architect. Surprisingly, his name is Buckminster Fuller, and he built an exhibition hall, which was called a geodesic dome. And that dome was like where people could walk around, a huge structure, but it has that shape like that with these panels. If you look at this closely, it's a series of hexagons with 12 pentagons that interlink and hold the whole thing together. What is a staggering coincidence in chemistry, that natural molecule of carbon is actually the perfectly similar configuration to a football. It is hexagons that are joined with those black pentagons there. I find that quite an awesome coincidence. I mean, that's just what nature came up with, because to make a football, those pieces of leather panel create a nice tidy sphere, and nature came up with the same idea with a carbon molecule. Okay, there are also bigger molecules. There are C70 and even bigger ones. In medicine, this might be used for trapping medicines which can slow release in the body. This can also be developed into kind of hypodermic syringes which could inject individual cells. The future for that material is very exciting. In the UK, we have a very proud record of science research. This buckyball was discovered by Harry Kroto in 1985. He was a resident professor at the University of Sussex, and he received the Nobel Prize for this discovery along with two other colleagues. Okay, so very recent, very exciting. That wasn't known about in the 1970s. It was my privilege to have met Harry Kroto about 15 years ago on a chemistry course. We took some students into central London, and he signed his autograph, and I've got a copy of his autograph, so quite pleased about that. I want to now focus on simple covalent molecules and rationalise their shape. Okay, so the way we rationalise the shape of simple covalent molecules is to follow a few simple rules. This is known as the electron pair repulsion theory, and it gives very reliable predictions. You count the number of electron pairs around the central atom. You then assign the electron pairs moving to a position of minimum repulsion. They go to maximum spatial orientation or minimum repulsion. This will become clear in a minute. Now, there are different types of electron pairs. What's called lone pairs. Lone pairs, they have the strongest repulsion. Lone pair bonding pair is the intermediate repulsion, and weakest is bonding pair, bonding pair. I'll explain what those terms mean through the examples. Okay, so let's just kick off with a simple example. Beryllium chloride. To be able to do this exercise, you need to be quite good at your dot and cross diagrams. Remember, you need to know which groups the elements are in and to get your electron counting up to scratch. Beryllium is in group 2, so it has 2 outer shell electrons. Right, now the focus here, don't worry about those 6 electrons around each chlorine. It's these 2 pairs of electrons here, and those are called bonding pairs because they bond the beryllium to the chlorine. Right, so you could ask quite a young student this, where would negative charges, similar charges, where would they have to move to minimize the repulsion? And you can simulate this with your arms. If my 2 hands are negative charges, where will they go to minimize the repulsion? And the answer is out there like that. Get them as far away from each other as possible. So I've got one bonding pair there and another bonding pair over there. We can't do any better than that. As soon as we start to close the angle up, we're increasing the repulsion. So this molecule has a linear shape. The bond angle in there is 180 degrees. So that molecule is linear and straight. Lone pairs are when you get extra electrons hanging around up there. We haven't met that yet. Before I move on to a different example, I just want to mention another molecule, carbon dioxide. The bonding in carbon dioxide, we have 2 double bonds. Right, this is where you need to know what group your elements are in. So if those crosses are electrons for carbon, carbon is in group 4, which means it has 4 outer shell electrons, 4 valence electrons. Those are the 4 crosses. Oxygen is in group 6. So those 6 dots belong to oxygen, and we don't need to worry about these over there. That's just bits of stuff out in the wings. It's not impacting on the discussion. I've got double bond there, double bond there. The question is, what's the shape of that? And again, you can see it's all nice and symmetrical, and so again, it's another linear molecule, 180 degrees across there. Let's move on to something different now. Boron trichloride. Boron, you need to know your periodic table, is in group 3. So it has 3 outer shell electrons. Okay, and again, I'm not worried about all these peripheral chlorine electrons there. The significant issue is these 3 bonding pairs around the boron here. Okay, so how would you minimize the repulsion between those 3 bonding pairs? And most students will come up with the idea, put them into a triangle, and that's exactly right. So it looks like this. And the bond angle, just dividing a circle into 3 parts, makes it 120 degrees. The molecule looks like that. It's a flat molecule. Anything that's flat in chemistry we call planar, and it's got 3 corners to it, so it's a trigonal planar shape. There, that's the linear beryllium chloride. You can see the nice straight line with no lone electron pairs in there. So BeCl2, carbon dioxide, and there are other examples as well. Okay, so this one is boron trichloride. Right, so what we're going to do, we're going to develop this up. We're going to put more and more electron pairs around the central atom, and then it will start to get more complex when we have lone pairs. So that's where we're moving to. And at the end of this exercise, I'm going to give a short list of covalent molecules and ask you to assign the shape to them so you can apply your knowledge and see whether you can decide what shape they are. Okay, so my next example, I'm going to use methane. This is natural gas. It's the first in the alkane series. So this is CH4. So carbon in group 4 has 4 outer shell electrons, could be those 4 crosses. Hydrogen only contributes 1. So a nice simple dot and cross diagram there. I find students stumble when I say, what do you think the shape of that is? They think it's a flat sort of cross like that. Well, you know, we can do a lot better in terms of minimizing the repulsion than that. These are 90-degree angles here. You know, if we take the thing into 3 dimensions, we can minimize it a lot more. The shape that we then achieve is this molecule here. This molecule here is a tetrahedron. It's the shape of a methane molecule and many other molecules. So by moving the 4 bonding pairs into 3 dimensions, I've minimized the repulsion to its limit. I can't do better than that. And that might be ringing a bell that the diamond structure is made up of a whole stack of those going right the way through the crystal. So that tetrahedral shape permeates the whole of that molecule. The molecule itself is tetrahedral in shape, whichever way around you turn it. You think of a triangular base coming up to an apex. That is a tetrahedron. It's a pyramid that has a triangular foot coming up to a point. That's a tetrahedron. I must stress the way you draw this is quite important. Examiners will get a bit impatient if you don't try and show the three-dimensional nature of it in your drawing. So if I put a hydrogen up there and then this line coming out there, this is the molecule sticking out of the board. It's a bit like if you're looking down a railway line, this is sticking out towards you, and then I've got one in the plane of the board and then one behind the plane. So that's going behind the board, sticking out. These two are flat in the same plane as the whiteboard. Okay, so this is tetrahedral. The four bonded pairs all move into a tetrahedron. And very difficult question, unless you're pretty good at your maths, you won't be able to quickly discern what the bond angle is in there, but it's one you need to know. It's 109.5 degrees, 109.5 degrees. Okay, so all of the angles in there are all 109.5. All of the angles in that diamond, which is related to this, are all 109.5. Okay, so that's a classic example of a tetrahedron there for methane. I'm going to now look at an example with 5 bonding pairs of electrons. Next example, there's not many more to go, and there's a reason why there's not many more to go. Phosphorus pentachloride. Phosphorus, all you need to do is look at your periodic table. Which group is phosphorus in? You don't need to sort of work out the shell order. It's in group 5, which means it has 5 outer shell electrons. As I said before, those electrons there are not critical to the discussion. The point here is that I've got 5 electron pairs. I can make it a bit more regular. 1, 2, 3, 4, 5. A tough question. How would you minimise the shape? Students kind of wrestle with that. I'll say, right, you've got 2 minutes to work out what you think the minimum repulsion for 5 electron pairs is. And we get some very weird and wacky ideas. And in fact, it's quite an elegant, simple shape. It looks like this here. I've got 3 chlorines in a flat plane in the middle, and 1 above and 1 below. Okay, these are called equatorial and these are called axial. That's just a detail. Okay, and if you spin it on the table, it makes quite a little good spinning top, but that's a trivial distraction, but students quite like doing that too. Right, so how do we draw that? Chlorine, chlorine, chlorine. 3 chlorines in the flat plane, those 3 in the middle there, just in that flat plane. They're planar, those 3, and then 1 above and 1 below. And I then ask students, what is the name? Think of a logical construction for the name of that. It's related to something we've met before. It's got a little triangular pyramid there, but it's got a pyramid underneath. So it's a trigonal bipyramid, trigonal bipyramid. So if you think of 3 points coming up to an apex and the same underneath the triangle, you can sort of put these lines in to give a sense of the bigger shape of it, but it can get a bit messy as well. And 1 going down there as well. So nice and regular. Bond angles, not particularly difficult to work out. These angles here between the plane in the middle and the vertical is 90 degrees, and then those angles in there are 120 degrees. Okay, so trigonal bipyramid. I have one more example to look at in terms of bonding pairs. If you think about it, there must be a limit to the amount of bonding pairs you can get crammed in, because if you think of electrons all shoved together in a confined space, electrons don't like each other, they're all very repelling. So the next example, 6 pairs, is almost the limit. There is actually an example where you can have 7, but for the A-level course, 6 pairs of electrons around the central atom is the limit, and let's look at that shape. Okay, so the sulfur hexafluoride. By the way, you need something as powerful an oxidizing agent as fluorine to get sulfur to do this reaction, because you're getting sulfur to go in what we call a +6 oxidation state. When you do redox chemistry, you'll know that a +6 oxidation state means that you've made it join with 6 fluorines, and 6 electrons in the outer shell of the sulfur are being pulled away towards the fluorine. Fluorine is able to do that. It's a very powerful oxidizing agent. You would struggle to get that to happen with chlorine, but that's really another topic. The topic we're dealing with here is that there are 6 bonded pairs of electrons. Where would they move to minimize the shape? And again, don't produce some awkward, wacky shaped molecule. What we get is this molecule here, which has 4 fluorines in a square plane, and then one above, one below. And that's an octahedral molecule. Octahedral because if you covered it with paper, it would have 8 sides to it. It's like 2 Egyptian pyramids base to base touching each other. Okay, so very, very simply, all the bond angles are 90 degrees. There's no confusion about that. Sulfur in the middle, 4 fluorines in a square plane. It would help if you just show these perspective lines a little bit. You could do those as broken lines as well. And that one is octahedral. And all the angles are 90 degrees. You might be saying, can you get 7 pairs of electrons in? IF7 is a molecule, but this is off the A-level course. And if you start to crowd in more and more electron pairs, they don't like each other. They get very uncomfortable being pushed together because they're all negative. Similar charges repel each other. So 6 is the example, is the highest one we look at on the A-level course. Right, now the last thing to look at is a couple of examples where we've got lone pairs of electrons. And this creates a more subtle shape, and we'll rationalise that now. Ammonia, alkaline gas, really important to make fertilizers for agriculture. But looking at the shape here, again, don't fumble with the number of electrons. Nitrogen is in group 5. It has 5 outer shell, 5 valence electrons. So 3 of them are used to bond to the hydrogens, 3 of them are employed with the hydrogens, and then there is another pair of electrons up here, which is what we call a lone pair. It's not bonded to anything. So what is the shape of that molecule? The way to discern that is still think of it in terms of 4 pairs of electrons. Now 4 pairs of electrons gave us the tetrahedral shape like that. So if I just pull off an atom there, this time instead of it being an atom, it's a lone pair up there. Now I said at the beginning, one of the rules of this exercise is that the lone pair has a particular greater repulsion. The reason why the lone pair has a bigger repulsion is that it's sat very, very close in. It's close in here. It hasn't been teased out by the atoms it's joined to. So because it's close in, it's extra repelling. The lone pair has this extra oomph about it in terms of repulsion. So when we had the tetrahedron, you will recall the bond angle was what? We said the bond angle was 109.5 degrees. Now, that lone pair up there, it pushes these 3 bonds, these 3 legs down, pushes it down to 107 degrees. Okay, so there's a nice little model of ammonia there. The lone pair is invisible. If you want, you can draw that just to, often you'll see that in textbooks. And the angle now has been diminished to 107 degrees there and there. So the angles between the hydrogen-nitrogen, a really silly mistake I sometimes see people do, maybe they get a little bit stressed in the exam, and they'll put an angle here between the lone pair and the hydrogen. That's nonsense. The lone pair is just an invisible bit of the molecule. The angles are between the hydrogen and the nitrogen and the hydrogen, and that's 107 degrees. You know, there's nothing wrong with putting that lone pair up there just to signify it's up there. And then we have to assign a name to that, so a bit of creativity here. What do you think we could call that? We call it a trigonal pyramid because it's got 3 legs and it is a little pyramid, so trigonal pyramid. You could call it a distorted tetrahedron because if you think about that, that shape is actually a triangular based pyramid like the tetrahedron, but it's not a proper regular tetrahedron. So you need to be cautious if you use that term. It's a distorted tetrahedron. Very famous example, it's one that examiners love to ask you about. What is the shape of ammonia? Give the bond angle and give the name of that shape. Okay, so 1 lone pair, it pushes those bond angles in. A bit like an umbrella closing. You think of an umbrella up there and then it gets forced down by that lone pair sat on the top. Okay, and the reason why it's very good at pushing them down is because it's close in. It's right down snug on top of the nitrogen and it exerts this extra push. Okay, there's one more really important example, and that's water, and let's look at the lone pairs in that molecule. It is believed that we do not fully understand the structure of water. Something as common, as well known, as essential to life, we still don't understand the structure of it properly. With chemistry, our knowledge is a bit of an iceberg. We really only know so much. Anyway, that's a digression. Coming back to this here, the water molecule has 2 lone pairs because oxygen's group 6, so I've got 6 crosses around there, 6 crosses, and the 2 dots for the hydrogen. The mistake students make, as soon as I say, what is the shape of that, they just fall flat on their face and think, well, that's so symmetrical, that all looks such a nice pattern as it is, they think it's linear. They think that the hydrogens are going to sit out there like our beryllium chloride. Absolutely no way. When you say that, you're ignoring the two lone pairs. We've got to minimize the repulsion. And let's go back to that tetrahedron. When we had 4 pairs of electrons, remember tetrahedron was our way of minimizing that. So if you can imagine that these go into some variation of a tetrahedron. We have oxygen there, 1 bond there, 1 bond there, and then 2 lone pairs sat up here. Looks almost like a cartoon character, but it's not, it's a molecule. So these are the lone electron pairs. Okay, and so the shape of that molecule is, we describe it as bent or V-shaped. It is absolutely not linear. You're ignoring the lone pairs. They're having a whacking great effect. 2 lone pairs which are repelling each other enormously and pushing those hydrogens right away. So what about the bond angle then? Remember the tetrahedron was 109.5. The ammonia shrank to 107. We've now got 2 lone pairs. We've got, we're ramping it up now. So this bond angle shrinks down to 104.5 degrees, 104.5 degrees. Okay, and there are other molecules with that bent shape like that, and that's achieved by, having usually 2 lone pairs. Just before I finish, I need to show you this beautiful model here. This is an ice structure. Ice is H2O, that's formed into this beautiful regular solid arrangement. If you look at that, the red spheres are the oxygens, the 2 whites are the hydrogens. So the little triplet shapes there are the waters. These purple things here are not bonds, they're not proper bonds, they're called hydrogen bonds, which is a kind of a weak arrangement between one molecule and another. But what is staggering about this, I wanted to mention this, is that this structure is less dense than a pile of water molecules, with the effect that ice floats on the top of water. So ice cubes in a glass float on the top. When rivers freeze over, the ice forms on the top, and so the aquatic life underneath can survive. If ice was more dense than water, it would freeze at the bottom and completely solidify the river. Right, this is where it gets very, very attractive. If you look at the shape of that ice structure there, it has a remarkable similarity to a diamond structure. Chemists talk about these hexagonal holes, these hexagonal shapes, and also the transparency. You can see through those tunnels there. Exactly the same with diamond. Diamond has these hexagonal holes, and that's why diamonds are transparent, because light can pass all the way through those shafts, all the way down from one side of the crystal all the way down to the other. So it's a very transparent, open structure. Final point about this, that spacious arrangement. Imagine a marquee going up in the summer, a tent going up. When ice freezes, it forms this spacious arrangement which takes up less space than the water molecules, so it's less dense than water. When the ice melts, that collapses like a souffle into a pile of water molecules, which are more dense. Okay, so it's a nice feature that ice freezes into that regular diamond-like structure. We've covered all the main examples of simple covalent molecules, and I've related it to a couple of other aspects. Hope you've enjoyed watching this. I'm just going to finish off by putting down a couple of examples that you might discern what the shape is, but I won't talk about them in this short video. Right. Some examples for you to look at here. Now, mistake students make, they just look at it very naively. They just look at the number of atoms and say, oh, it's that shape or it's that shape. And you can miss the point very easily if you're not accounting for lone pairs. There are lone pairs buried in some of these examples. Some of them you might think should have lone pairs and then don't have lone pairs. I'm not going to give the game away here. Silicon tetrahydride, hydrogen sulfide, that's the gas produced from bad eggs, rotten eggs. Nitrogen fluoride, ammonium ion, hydroxonium ion, sulfur dioxide, that's a common air pollutant. PCl3, SO3, PCl4+, PCl6-. I'll leave you to ponder on those examples, and I might provide the answers in a later video. Thank you for watching.